Okay, so if you feel like the world of AI is moving so fast that you need a scorecard just to keep track of all the acronyms, LLM, VLM, SAMUR, definitely not alone.
Oh, absolutely not. The information overload it's just intense.
And trying to keep up with every single new specialized model, it's practically a full-time job.
It is. And, the sheer pace of it all means that the foundational tech is constantly being specialized. For most people, AI is still this one massive, mysterious black box.
Mm.
They know what it does. It generates text, it captions an image, but they don't really know how it decides which tiny task needs which specialized tool.
Right. And that is exactly our mission today. We are grabbing the keys to the engine room to give you that expert shortcut. We got our hands on this fantastic deep dive demo that lays out 8 foundational specialized AI models.
Yeah.
These are the crucial building blocks that are truly revolutionizing how AI processes all this complex, unstructured data, whether it's text, images, or even a mix of both.
And these models are not interchangeable. That's the key thing the source material emphasizes. They all serve really distinct purposes,
Okay.
but they're all foundational to the advancement of AI. Each one is designed to process different data inputs way more efficiently and more accurately than a single generalist model ever could.
Okay, let's unpack this then. We're going to clarify what these 8 models do, why they even exist, and how they all work together in harmony. Because knowing their names and functions, that's a massive insight. It gives you a real understanding of modern AI architecture. And we're going to start right where most of us began our AI journey, with the core language trio.
Absolutely. We have to start with the baseline, the one everyone knows, the large language model, the LLM.
So what's under the hood of the LLM? What makes it our starting point?
Well, the input is fundamentally just text. That's it. And its key components involve tokenization, which is just breaking language down into digestible pieces,
That's right.
embedding, and that transformer-based architecture we hear so much about.
And the output application is what we see every single day, running billions of times a day. It's processing massive volumes of text to generate output that makes sense in the context of language.
Exactly.
So this is your go-to for basic tasks. Straightforward text generation, translation, summarization.
That's right. But the LLM, as powerful as it is, can sometimes struggle with nuance.
Yeah.
If you feed it a 50-page legal brief, it might lose the thread of the core argument
Why is that?
because it just treats all the text as one continuous stream. And that's where the next model steps in to really enhance comprehension, the language context model, or LCM.
Okay, so how does the LCM solve that problem, that lost context problem?
The input is still text data, but, and this is crucial, it uses sentence segmentation. It's not just treating the text like a giant scroll.
Ah, so it's actually reading it in meaningful chunks, like paragraphs and sentences.
Precisely. It understands that the context of one sentence ends before the next one begins, which sounds obvious to us, to a human, but for an AI, that's a huge leap in understanding the structure.
Yeah, that's a really big deal.
It is. So its key components include that segmentation, along with something called sonar embedding. And that combination allows the system to process these chunks of text that have a definitive, meaningful boundary.
So it's better for complex stuff.
It provides the heavy lifting for detailed natural language understanding and complex queries where all that nuance is just paramount.
Got it. So if I'm building, say, an internal knowledge base where I need the AI to answer really specific questions based on hundreds of complex documents, the LCM is doing that heavy lifting to make sure the system really gets the nuances in the source material.
Precisely. And if the LCM gives us that detailed text comprehension, the third model in this trio, the LAM, the language and model, that takes us into the realm of action and memory. It's the contextual learner.
Wait, hold on. If an LLM generates text and an LCM understands complex context, why do we need a LAM? What makes it so different from, say, just a long context LLM?
The difference is really in its input processing and its internal architecture. A LAM handles text and perception-based inputs.
Perception-based. What does that mean?
Things like metadata, or signals that convey spatial or temporal information. More importantly, it integrates intent recognition and a perception system that helps it recognize complex patterns in real-time language and action.
Okay, so if I ask an AI assistant to remember that thing I did yesterday and apply it to this new email, that's LAM territory. It's moving past just processing text towards real-world input and tracking things over time.
Exactly. The source highlights that it integrates deeper levels of memory planning and feedback integration. Think of it like giving the model a temporary short-term memory cache.
Oh, Oh, interesting.
It tracks previous steps and integrates that history to inform what it does next. This is why LAM is ideal for these complex multi-step tasks that require contextual learning and prediction over a sequence of interactions.
That distinction is so important. It's the difference between an AI that can answer a single question and one that can hold a meaningful conversation over days or weeks.
Right.
But if LAM is so contextually rich and complex, the scale must be massive. Which brings us to our next model, which deals not with language, but with architectural efficiency.
We're moving from the cognitive function of the model to the physical challenge of running it. Let's talk about the unsung hero of massive AI infrastructure, MOE, the mixture of experts.
It sounds like a consultant firm for algorithms. How does MOE solve the scaling problem that a complex model like LAM introduces?
Well, MOE is fundamentally an architectural technique. It's designed for large-scale AI. So imagine a model with trillions of parameters, right? But only a tiny fraction of those are ever needed for any single query.
Right.
If you run every query through all those trillions of parameters, you burn an enormous amount of time and energy.
So MOE acts as a kind of gatekeeper.
It does. The input can be text or other data, but the key component is the router mechanism. This router dynamically looks at the incoming request and decides which expert model, from a set of specialized smaller experts, to consult for that specific task.
That's a huge insight into efficiency. So instead of lighting up billions of unnecessary parameters, the router just picks the 3 or 4 best-suited experts for that specific input.
Exactly.
That must translate into enormous cost and energy savings. That's the real business application here.
Absolutely. The model features expert selection and then a weighted combination of their outputs, like a smart averaging of the best ideas from those selected experts. This is why the massive foundational models you use every day can respond so quickly and efficiently.
It's specialization at the architectural level.
Exactly, for both speed and accuracy.
Incredible. Okay, speaking of efficiency and different inputs, let's bridge the gap between language and vision with the VLM. This is the first model in our stack that explicitly handles visual input.
The VLM, or Vision Language Model, it takes image data as its primary input, but it works simultaneously alongside text data. It's the essential bridge between the two worlds.
And the power here is that truly multimodal processing, right? The model doesn't just look at a picture and separately read the text. It processes them together as related information.
Yes. The key component is a vision encoder. This encoder processes the raw visual data and translates it into a language that the model's text components can understand.
So they work in tandem.
Simultaneously,
Oh.
integrating meaning across both data types.
So if I show the VLM an infographic about, say, the economic history of a region, and then ask it a complex financial question about that image, the VLM sees the visual data points, processes my text query, and generates a descriptive text answer. It's the ultimate visual translator.
It is. It synthesizes meaning. It's ideal for complex applications like generating image captions, summarizing video content, or answering visual questions that require understanding context, like identifying the relationship between two objects in a scene.
Okay, so moving into our third section, we're going deeper into text optimization. We're focusing on prediction and sequence coherence. We have the SLM, the sequence language model. So if the LLM is general language and the LCM is context, what exactly does the SLM optimize for?
The SLM focuses purely on the uninterrupted flow and coherence of long text outputs. Its input is text, and its key components are compact tokenization.
Which makes the tokens smaller, easier to handle in a stream.
Right, and highly efficient transformers.
So its main job is sequential coherence. Why is that distinction important compared to a regular LLM?
Well, if you're using an LLM to generate a single paragraph, that's fine. But if you're asking it to draft a coherent multi-chapter business proposal or generate thousands of lines of code.
Where the context and flow have to be maintained across huge distances in the text.
Exactly. That's where SLM shines.
Yeah.
It's specifically optimized for sequence prediction tasks, where the order and the continuity are critical to maintain a narrative thread.
That makes a ton of sense. The SLM makes sure the flow of the story stays intact. Okay, so if SLM is about generating things in order, the next model, MLM, the masked language model, this feels like a contextual detective.
That's a perfect description. The MLM uses this unique process where its input is text, but the key component is something called token masking.
Which just means portions of the input are intentionally hidden from the model.
Exactly. During the training phase, the model is tasked with predicting those missing parts. Think of it as a constant game of Mad Libs.
Yeah, right.
By forcing the model to guess what should be there based only on the surrounding context, You enhance its ability to predict missing words or context extremely well.
This sounds incredibly useful for real-world applications, like data imputation or text completion where you might have gaps in your source material.
Or if a user accidentally skips a word in their prompt.
Yeah. It forces the AI to be a contextual expert, identifying necessary information even when it's incomplete.
It does. It trains the model to understand the context surrounding a blank space, making it highly robust in predicting missing information and cleaning up messy data.
So we've covered 6 models dedicated primarily to text, context, flow, and efficiency. That brings us to our final specialized model, the SAM, and then we're going to put all 8 of these puzzle pieces together.
Yep.
SAM, Segmentation Anything Model. Based on the name, this sounds like pure image processing, zero text.
It is the dedicated image dissection specialist.
Yeah.
Its input is primarily image-based, using a prompt input, which could be a simple mouse click or a text request like select all the cars.
And what does it actually do? How is it different from VLM, which also processes images?
VLM is about understanding the image and translating that understanding to text. SAM is purely about structuring the image. The key component is the image encoder, which converts raw image data into usable segments.
Usable segments.
This was a monumental breakthrough because standard segmentation used to require custom training for every new object type. Cars, people, surgical tools, you name it.
So SAM lets you identify and separate objects in an image instantly, even if it's never seen that specific object before.
Precisely. SAM is incredibly useful for segmentation tasks, where the entire goal is to break an image into meaningful parts.
And this is essential in critical applications.
Oh, absolutely. Object detection in autonomous vehicles, or most critically, in medical imaging, where identifying and separating different components within the image, like tumors or healthy tissue, is key for accurate analysis.
Wow. So we have the full stack models that handle pure language, LLM, LCM, language with contextual memory, LAM, architecture for efficiency, OA, bridging vision and text, VLM, predictive text, SLM, MLM, and specialized vision with SAM.
That's the set.
Now, what's fascinating here, and what the source really drives home, is how these systems work in harmony. The true power is the synergy.
It truly is. These models are not deployed in isolation. They're orchestrated to address a variety of complex, multi-layered AI tasks. For example, let's say you wanted to build an automated assistant that watches a user's workflow and then summarizes what they did.
Okay, that's a complicated task. Multiple steps involved there.
Yes, so you might use the VLM and SAM to watch the screen and process the visual inputs, whereas the mouse, what objects are on the screen.
Okay, got it.
Then you'd use the SLM to track the sequential flow of the user's actions over time.
Right, the sequence of events.
And the output of those models then feeds into the LCM and LLM to generate a coherent, contextual summary of the entire session.
That really shows the specialization feeding the overall capability and the architectural support. Where does MOE fit in?
The MOE acts in the background, making sure that when the system transitions from a vision task to a language task, it efficiently routes the request to the relevant experts, rather than burdening the entire system.
And LAM.
And the LAM might be used to maintain the memory of the session, making sure the summary output references the start of the session correctly.
So the overall goal here isn't just to build one massive generalist model that does everything kind of poorly, but to select the appropriate, highly specialized model or combination for the specific task at hand.
That's it.
That specialization is the shortcut to efficiency and accuracy.
That is the conclusion. By selecting the right model, or the right combination of models, AI systems become far more efficient and far more accurate in processing all this diverse data, leading to better outcomes in everything from complex natural language understanding to specialized image analysis.
And that brings us to the end of our deep dive. What a journey through the acronyms. We've gone from foundational language processing, LLM, LCM, LAM, to architectural efficiency with MOE, multimodal integration with VLM, predictive text via SLM and MLM, and finally, specialized vision with SAM.
The key takeaway really is that this specialization provides organizations with the exact tools they need. Tools to tackle everything from complex language understanding to precise image segmentation and sequential prediction.
And as you reflect on this landscape of specialized knowledge, remembering that MOE uses that intelligent router to select experts for efficiency, and LAM integrates memory planning for deeper contextual learning, it raises an important question for the future of scaling AI.
Right. If the current innovation is routing input through models optimized for general domains like text or images, the next frontier will surely build on that specialization.
So consider this. What happens when AI systems start routing input not just through models optimized for generalized inputs, but through models optimized for completely different niche domains of specialized human knowledge?
Mhm.
Say, a model trained only on patent law, or a model trained only on deep-sea marine biology. That's something for you to mull over as we watch the engine room of AI continue to evolve.